because they just simply don't do the assignment correctly or have no idea what's going on. So that's got to be kind of taken into consideration. How do you mark someone who's off by 1 cycle versus someone who's off by 1,000,000, right? So you would think it wouldn't happen, but it happens. So every year someone always throws me something new. Someone asked about assignment. Oh no, someone sent me an email about assignment 3. Yeah, I haven't posted assignment 3 grades. Yeah, I'm aware of that. Oh right, yeah, but you know, again, if you're using the simulator correctly, you know, you shouldn't be off at all, right? You should be dead on. In fact, you don't even need to use the simulator to be dead on, right? If you kind of sit there and measure all the cycles and you kind of work it all out. Again, these devices aren't meant to be mysterious, right? They want you to know what's going on, you know, and you can use these things to adequately create timing pulses, like consistently, reliably, right? Where there'll be no deviation whatsoever. That's what they're intended to do. So, but with the simulator, yeah, you should, I mean, all of you should get the value, you know, dead on. If you do the math and work it out, sure. You basically have one unknown. And I've given you that value, right? I gave you all some, you know, number to start with, and when you use that number and work it all out, you should be able to get it. All right. Okay, if there's nothing else, we'll move on here to discussing the stack pointer register. All right, okay. So the stack pointer register, this is just a register that just points to where the current stack value or current stack entry is. The stack is basically just it's a portion of RAM that we reserve for temporary storage and retrieval of information. So this is common to see this in CISC processors. Because we have such limited instruction, or I should say register space, right? We only have, particularly in this CPU, only 4 registers. Other registers of you know, even the Intel 8086, the original, and even subsequent versions only had a handful of registers. They don't really have a lot because of, again, the idea of the way CISC processors are made. You want to have the instruction opcode specify the register you're using, as opposed to using extra bits to specify the register you're using, and that would take more memory. So essentially the way it works is each time a word is to be stored in the stack, it's placed in the address 1 less than the previous one. So the stack always grows downward. So our stack pointer is usually pointing at the top of memory, and it grows downward. So if I push word A and then I push word B, C, and D, as you can see here, the stack pointer decreases over time. So that's when we push something on the stack, and when we pull something or pop something, the term is used interchangeably, it goes the other way. So when I pop something off the stack, I'm going from the lowest spot. So then I would pop D off, or C, or B, or A. We can't specify what we want to pop off. It's just where we get it to push it on, and when we pop it off, where does it go, essentially. All right, so there's no tagging of the information here. So for example, if I push accumulator A on the stack and then push accumulator B on the stack, the CPU doesn't know that I pushed A or B, like it doesn't tag it, so it would remember it later that it was A or B. It's just simply a number. So then when I pop it off the stack, I basically say, where do I want this number to go? Do I want it to go to A or B, for example? Okay. So this type of memory is what we often call a LIFO memory. You may have heard of this before. It means last in, first out. So as it means the last thing you put in is the first thing that comes out. Well, it's up to you to keep track of what you push on the stack and what it was. It doesn't necessarily have to be, you know, it's rare that the register you push is actually important in terms of what register it was. You know, it's just a, you know, a piece of information, just like anything else. All right, so the stack pointer, again, it's a special memory address register. We saw that in our diagram before. So for the HC11 specifically, when a word is to be stored on the stack, it's stored at the location of the stack pointer. So the stack pointer is always pointing to the next available location. Okay, it's not the one that has the current entry, it's the next available location. So when a word is then to be read off the stack, it is read at the location of SP plus 1, right? So if I go back here, after I push D on the stack pointer would be pointing at 161, right? And then when I want to read something off the stack, it automatically adds 1 to it and then goes to 162 and then pulls that information off. Now, the rationale of that, I can't really say, because again, a lot of CPU manufacturers do this differently. Like, what is the actual stack pointer referring to? There could be this deviation, just to let you know. So always be careful about that. So again, on the HC11, the stack pointer is always pointing to the next available address. For different ones, it might be a little bit different. All CISC processors have a stack. You'll notice our RISC processor did not. The reason being, well, if you look at what for example, the operation of pushing something on the stack is, okay, so let's take this value of our register and let's write it to this memory location. It's actually several steps. So the benefit is the instruction is very small. For example, push A or pull A, it's usually a 1 byte instruction. That's a pretty economical way of storing something temporarily. If you didn't have the stack, you'd have to store it in memory somewhere with like an STAA and then an address or something, and that would take up, again, more instruction space, but probably less time. Okay, so the benefit here with stack operations is they're a small piece of code, but they tend to be slow. But we're not really interested in speed in that particular case. We're interested in, code compactness, and again, that's what these CPUs were designed for, is to use the least amount of memory for their code anyway. All right, so that's the stack pointer, and we'll talk more about the stack later. Going back to the registers, I talked about accumulator D. This is a way they often summarize registers in the textbook, or I should say in the reference manuals. So you'll see them all listed here. You'll see you have all these 16-bit registers here. Again, the reference starts at 0. Accumulator A and B and D are actually the same registers, right? They're the same. So if I change accumulator A, I'm changing accumulator D. If I change accumulator B, I'm obviously changing accumulator D. And if I change accumulator D, then I'm likely changing A or B. I'm not sure which one. It all depends which bits are changing. But these are the same register. It's just a different way of referring to the information. We have our index registers X and Y. They're equally the same, but do, again, remember every time you use an operation that uses the Y register, you're going to take an additional cycle, an additional byte of memory to encode that instruction. The stack pointer we just talked about. And of course, there's the program counter that, although we don't have access to it, we know where it is because we're writing the code that's using it. So again, all these registers, they're obviously different registers except for A and B and D, but they all have their particular purpose, right? They're all special purpose in some kind of way. Again, where RISC processors, they kind of threw that all away and just said all the registers are pretty much all the same. Okay. And then lastly, we have our condition code register here, where everything is kind of just, again, broken down on what it does in this way. Why they're showing us the order here, so I know the carry is in bit 0, the overflow is in bit 1, and so on and so forth, is because we do have an operation that allows us to take this, the condition code register, and transfer it to accumulator A. So then we can change the bits manually, and then we can transfer it back. So for example, I do have control over the carry and the overflow and the interrupt with particular instructions, right? I can change them pretty much immediately, but for everything else, I cannot. So if I want to set the disable bit or the X interrupt mask, I have to, have the value in the accumulator A and then transfer it to the condition code register. It's just because these values, they just change very rarely. Whereas, me changing the carry or the interrupt mask or, the overflow, that can be something that I do very often. So they have instructions for that. Again, different CPUs, they may take different approaches here, but this is typical of CISC processors of that era. Okay. So again, going back to the ALU in this case. So the ALU is taking in at least 2 pieces of information. It could be accumulator A, it could be accumulator B, it could be accumulator A and something from memory. It kind of all depends on what the instruction is, right? There's a whole variety of things it can be. Then we'll have some type of a control circuit telling us what we're actually doing. Are we adding? Are we subtracting? Are we, left or right shifting? Whatever it may be. And then, of course, there's some kind of result that comes out. Now, along with that result, we can have our condition code signals. H should really kind of be a part of this, but I didn't draw these figures. This is from the textbook. So these get updated, and the carry is the one that kind of often goes back in, as well as probably the half carry when certain types of operations are being done. And this allows us to kind of chain operations together to do larger pieces of arithmetic. So even though I can generally only add 8-bit numbers at once, I can chain those operations together to perform arithmetic on any size numbers at all. I can do 128-bit addition or 512-byte addition or whatever. It's just, it doesn't matter. I can keep chaining these operations together. And that's kind of a useful operation. It's not necessarily fast by any means, but it just means I can do it, right? And that's always a trade-off with CPUs. For example, 64-bit CPUs can do 64-bit arithmetic. It's just slower, right? It takes longer. And 64-bit CPUs can do even bigger arithmetic. It just takes longer. So that's why we generally write our code in, for example, 64 bits only, so that it runs as fast as possible. But if I try to bridge it out more and do bigger numbers, it's not going to be as efficient. You'll see a major performance impact, but at least it gets the work done, right? So, okay. It would appear I have a clicker question coming up here, so let's see what it is. Let's take a capture here, send it to your devices. So it is quite critical that before we use the stack, that we do initialize its value. I mentioned this when I talked about the XIRQ interrupt. And that's why it's called XIRQ and no longer the traditional term NMI, because that one had, again, its issues. Being that if you asserted the NMI before the stack pointer was initialized, well, where was stuff being stored, essentially? I mean, you could get around it by putting in some kind of in-circuit logic, that would stop the NMI from being fired before, a certain amount of time. But, that's not something we should be doing. The CPU should know better. So this was a problem early on in a number of CPUs. Okay, as I recall, there were 82 people in the class. I'm going to stop it there. I'm not going to wait too much longer. Okay, so this is our RAM space. So where should the stack pointer be initialized to? So if you remember, what is the stack pointer pointing to? It's basically pointing to the place where it's going to store a piece of information or the next piece of information, right? So let's take a look here. And, well, where is the valid location? Well, the highest location would be 1FFF, and that would be the place to definitely put it. I mean, you could stick it anywhere, but the problem is as we add things to the stack keeps decreasing, right? So if I store it at 0000, for example, the first value I push on the stack would go into RAM, but where would my stack pointer go next? It would go to FFFF. And what's generally there? Well, there's ROM, for example. So there's nothing wrong with trying to write to ROM. You can do it. Well, you can try, but nothing happens. So when you try to pop that value off the stack, then you're going to be reading the value from ROM and not what you actually wrote. And the number isn't going to be correct, and that's going to cause a series of cascading failures, right? So the same thing with 2000. If this is a ROM address, the first number you push to the stack, it won't be written. And whatever you get back when you pull it off, it will be something else and something you're probably not expecting. And it will cause the system to be, tainted in some way. And it doesn't take much, right? As I said, it only takes one bit to go bad before your system essentially fails. It'll fail eventually, I'll say. Okay. So there's a number of operations the ALU can do with just single values. We often call these unary type operations. Just means there's only one input in, and being that it's CISC processors, the input is often one of the accumulators. So when you see me using accumulator A often here, for example, this is the terminology or syntax we use often just to kind of explain what's going on. Often later on in the slide, you'll see like accumulator X, for example, meaning the X can be interchanged with an A or B. Often with most of these things, they can be interchanged. So these are often operations we use, for example, clear, that will set all the bits to 0. So this is a smaller instruction, right? Clear would just be a single opcode, no operand, right? Whereas, loading accumulator A with a 0 would require, the opcode and then the operand. So this is much smaller and it runs faster. Complementing, that inverts all the bits. That's also another instruction we'll see. Negating, this will generate the 2's complement of accumulator A. I can do the same thing by loading accumulator A with something, then subtracting a number from it, right? So it's effectively this operation in the CPU. However, that takes more bytes, right? More instructions to do. You'll also see increment accumulator A, for example, or decrement accumulator A. Actually, I don't think the HC11 has an operation for that. No, it does. Sorry, it does. I'm thinking about another CPU. So yeah, dec A or inc A, for example, it has that. And we also have some more useful things. For example, when we want to move information back and forth between, for example, our 16-bit operands, we do have an exchange operation that will exchange, for example, index register X and accumulator D, because they're both 16 bits. You can't do that with accumulator A or B and X because, again, they're not the same size individually. You have to do it with something that's also 16 bits. So with all these operations you see here, and this is typical of CISC processors, you can do all of these instructions different ways. It's just they've created these specific instructions because it's faster. It's faster in the sense of it's smaller piece of code, so fewer bytes, and fewer bytes means it can run quicker. So again, that's the underlying strategy of CISC processors, is to always make instructions where there's always a more efficient implementation of them, even though you can do it another way. So often you'll see with CISC processors and compilers, there's an option to say, oh, how do you want to generate code? Do you want to generate the smallest code? Do you want to generate the fastest code? Do you want to generate something kind of in between? Because that's something we were concerned with at that time. We wanted smaller code. Now that's not really the thing, right? Everyone wants faster code, so we're not really concerned about memory space. But with RISC processors, they took the other approach and just said, well, let's just make an instruction that does what it has to do and make them all the same, essentially. So we threw away this idea of making instructions as small as possible in terms of, in favor of making the hardware as simple as possible. Okay, so these are, those common things that we'll see. So when you look at the HC11 instruction reference, you'll see there's a lot of instructions there. But, it doesn't necessarily mean you have to use them all, right? It's just if you're trying to code something as small as possible or as fast as possible, you might want to try these different ones. And we'll see a number of instructions where they've done that. Another thing the ALU does when we start looking at other operations, shifting is a pretty important thing. I've talked about this a little bit. We have logical shifting. So whenever we do a logical shift, either left or right, whenever we shift something out, so for example, B7 is going to go into the carry. that's when we're shifting left, or if we're shifting right, B0 will go into the carry. But what comes in is always 0. This is one of those things that we call logical shifting. The incoming bit is always 0, whereas the outgoing bit goes to the carry. Now, the opposite of that, well, I won't say the opposite, but the alternative is what we call rotate. Now, the term rotate is actually poor. I don't know why they selected it. It doesn't actually rotate the carry around. What it's trying to illustrate here is, so when I do this shift, B7 is going to go to the carry, but the current carry will go into B0. So the current carry goes into B0, but then B7 goes into the new carry. So the rotate operations, they take in the carry and they generate a new carry. But when they draw it like this, it appears that there's, you know, this actual rotation going on, but that's not actually the case. All right. It's just kind of like, I don't know, I'd call it poor terminology, but it's what it is. That's what we have now. Yeah. Anyway, so the other option is with logical operations. This works fine with unsigned numbers, but when we get to signed numbers, then we have a little bit of a problem. And the problem that comes up is, well, what happens if you're doing a right shift, right? And the problem with signed numbers is that the highest bit, in this case bit 7, is always the signed bit, right? So if I were to do a logical shift right with a negative number, a 0 goes into the signed bit, and all of a sudden my negative number becomes a positive number, and that's not something that's supposed to happen. So we don't want that to happen. So we have an arithmetic shift right only, where it preserves the signed bit. So this bit stays whatever it is, and then, you know, the outgoing bit goes to the carry. So the incoming bit is not a 0, it's actually whatever it was. So it doesn't actually replace it. So this is very useful for signed numbers. Now, as far as the right shift, it's the same as the logical left shift. There is no difference. So if this is a large, well, I won't say a large number, but let's say this is a positive number at some point, and I keep shifting it and shifting it and shifting it. Let's say I have a bit here in B6, and then I shift it to B7. Well, my number went negative, and that's bad, of course, but there's nothing I could have done to avoid that. You know, I'm taking a number and I'm multiplying it by 2. It went out of range. I generated some kind of overflow. It's unavoidable, right? It's just going to happen. So if I take 1, multiply it by 2, I get 2, 4, 8, 16, 32, 64, 128. Well, I've just exceeded my range. Oh, well, you should have known better. There's nothing we can do to prevent that. So you should just simply know better is kind of like the opinion here. Okay. So do keep those in mind. So you'll often see those in these in CPUs, the different type of shifting. All right. What else do we have? Okay. Oh, hold on. How come there isn't? Right. Well, this is a problem with higher level languages, right? Because you start not being aware of how the CPU functions. And we don't necessarily want that. So this is kind of where that kind of falls apart, where, well, how do you know if your CPU has a carry or not? Can you rotate large numbers? Can you, or, you know, shift large numbers in these large changes? So when that becomes a problem, well, there's a simple solution in C. You have the ASM feature, where you can directly code in assembly language into C code. So when that becomes a situation, then you do it. Now, it's not to say that you can't determine if there would be a carry. You can certainly do like a bit mask before you do a shift and look at the highest bit and say, yeah, there'd be a carry there. That's a very generic way of approaching it. But you can't assume that the CPU you're using has a carry or has even support for determining that. Okay. Just saying, it's just what it is. C doesn't solve all the problems, but it kind of does a number of things. This is just where you're starting to get into very CPU-specific things. Okay, our two operand values are what we call our binary operations. And when I say binary, I don't mean, base 2 operations. I'm saying there's 2 inputs. You've heard the term unary, 1 input. Binary means 2 inputs. Again, it's poor terminology, but that's what they're implying by that. So obviously we have the ability to add numbers, right? This is produce the sum of the sum of 2 operands. So for example, something like this means add accumulator A, something in memory, put it in accumulator A. You'll often see anytime there's any type of ALU operation, the destination is often accumulator A or accumulator D, depending on the size of the operation. Okay, so clearly we can add numbers, we can add them in any order, right? When we subtract, well, we know how subtraction works, but do keep in mind the order of subtraction is important. So when I say subtract, for example, 10, I'm saying subtract from what I already have, right? So do keep in mind the term subtract in this particular CPU is subtract from, essentially. Some CPUs may differ in that. Again, I haven't seen them all. I've only used a handful of CPUs over my time, but it's possible someone could have thought, oh, maybe let's do it this way. It's better. It's possible. Multiply. The HC11 supports multiply, but it doesn't support it well. It doesn't actually have a hardware multiplier. It uses array addition. So if you look at, add and subtract, it takes basically 1 cycle to do the actual core of this operation. There's obviously, more stuff to read in the instruction and do all that other stuff, but multiply takes approximately 8 additional cycles, 8 cycles to do the work. So it's just doing an array multiplication. And I think I covered that in DLD1. So multiplies aren't fast, but, you can code it and it does do it, properly. Within a reasonable amount of time, better than if you had to manually come up with an operation or algorithm to do it. So for the HC11, it is an unsigned 8-bit multiplication. So it takes whatever's in accumulator A or B, and it multiplies it and puts the result in accumulator D, which hence, of course, overwrites accumulator A and B. There's no operands. It's simply just mul or whatever the mnemonic is for it. That's it, right? So this, again, is telling you we don't have options here. I can't say, okay, multiply this byte in memory with this byte in memory or something like that. It's strictly that simple. All right. We can also do an integer divide, but again, it's not a hardware divider per se. We're using the components of the ALU, for example, the add and subtract, to implement a division. And this is a very long operation. Multiply actually takes 10 cycles to run. The integer divide on the HC11 takes 41 cycles. So that's 41 cycles where your CPU is doing some operation, and that's a long time. But that's the price of being able to do something, but you may not want to do it that often. You only do it when you need to. So again, this is a fixed operation. I believe the mnemonic is just called IDiv. And it takes accumulator D and it divides it by index register X, and it puts the quotient in index register X, and it puts the remainder in accumulator D. Again, we don't have an option here on what's being divided by what, and that's not unusual for CISC operations. The same thing applies to the 80886. You have the same inherent limitations. Multiply and divide only work on particular registers. Okay, what else do we have? Compare. Comparing is subtraction, effectively, but no result is stored or saved. We only update the flags. So I should say, anytime we do these operations, all those flags are updated in some way. So every time we do an add, we update the 0, we update the overflow, we update, the negative flag. Add in particular will update the half carry as well. Subtract and multiply, all these things will update these flags. Compare also does the operation, but it doesn't save the result. It simply just updates the flags. So if I want to see if a number is bigger than another number, I simply just say, well, is A greater than B? I say, well, A minus B, what's the result? Is it negative? Is it positive? Or is it 0? And that's how we determine that. Hold on here. Someone has a question. Can the stack be of good use here? Like push whatever important information you want while you do there and then pop it back off. Right. So yeah, no, the stack is basically for all this temporary movement of data. And I'll talk about later where it comes into play. I believe I have some slides on that. Let me just look quickly here. I don't remember. Yeah, I have like 3 slides kind of explaining that coming up very shortly, why it's extremely useful. If you didn't have the stack, then you have this problem of saying, well, where do I store these things in memory? You need an absolute address, right? Where would I store this information? And that becomes a problem. So with the stack, it's not really your concern where it's being stored. You don't have to keep track of where it's being stored because it's up to the stack pointer itself, right? So we're kind of taking advantage of that. And I'll explain again very shortly why the stack is so useful. Okay, so with compare, after the compare, we would use all of our type of branch instructions, right? Branch if equal, branch if not equal, branch if carry is set, branch if carry is cleared, and all those things like branch if greater than, branch if, lesser than, or whatever. The HC11 has a whole lot of them, right? And again, it's not different than most CISC processors of the era. They had a lot of that. So we do the compare, and then we do our branching based on whatever we're looking for. And the last thing, of course, the LU does, it does all of our logical operations. Let me just move this over so you can see the rest of the text. But essentially, it, logical ands, or exclusive ors, all those types of things. And those are bitwise operations, right? So when you say and 2 values together, it ands the 2 corresponding bit zeros of those values. And then it ands the corresponding bit ones of those values, and so on and so forth. The same thing with the ORing and XORing. Right, so it's just doing a bitwise, as we say, operation. All right. Okay, it appears I have a single, I think, clicker question here. Let me just take a quick peek. How many there are? Actually, there's 3. So, yeah, they won't take too long. I think they're pretty quick. All right, so let's get to that here. Take a picture. You guys got it right now. This should be a quick one. Just kind of going through my emails at the moment, and I just noticed that sometimes my email is set up to flag messages from students. We have 90 responses now. Geez, where did everyone come from? But sometimes people send me emails from their Gmail accounts or some other accounts, and those don't get flagged so easily. So I try to answer the messages that are clearly highlighted first and foremost. I do have a number of messages from all over from my email, but I stress that if you can send emails from your uWindsor, that would be better because I see them easier. So otherwise, our system basically says, oh, it's from an external address. It's probably not trusted, right? It could be spam. And in fact, they often could be flagged as spam as well. So I'm just saying. Okay. So what's the value of, if I load in a 16-bit value of 1, 2, 3, 4 in accumulator D, what's the value of accumulator B? Well, if I go back a few slides, you'll see that accumulator B is the least significant byte of accumulator D. So the least significant byte is 34. So it should be, in fact, 34, or B. Okay. All right, here's another question. It's a quick one. I guess we're looking at about, what, 92 responses now? So if you're wondering what is ASL and LSL, well, again, just think about what it means. The SL is shift left, and the A is arithmetic, and L is logical, right? We try to use terms that are, easy to remember, but again, easy for the computer to process, right? And things we don't mess up when we're typing. Not that you can't, mess up ASL and LSL accidentally. It's certainly a lot harder to write arithmetic shift left versus logical shift left. We would probably often make mistakes there. And it's easier for the computer to parse these things, right? Okay, looking for about 20 more people here. If that, sorry. 10, really. Okay, I thought there was 92 before, but whatever. Okay, let's stop this now. All right, so what is the difference? The sign bit doesn't change. The sign bit acts as the new carry. The sign bit is shifted in, or nothing. Then why do we have two names? So I did discuss this. So this is shift left. So it's basically multiplying by 2. And if we keep multiplying a negative number by 2, we're going to get overflow, and it doesn't really matter. It's unavoidable. So the answer is actually D. There's no difference between them. In fact, there isn't actually 2 instructions. There's actually only 1. But our assembler will support the syntax of both and encode it properly. This is what we often call a pseudo instruction. So I'm not even sure what is the official one that the CPU refers to, but the assembler tool, the official one from the company, and third-party ones will all accept either and encode whatever the proper opcode is. So it's really just there for, just for simplicity, basically, right? You can put an either or, it doesn't matter. Okay, and I think I have one more question here. Yes. This one should go quick. I think you guys can get it in under a minute. I was hoping. Okay, that seems to be it. We seem to be losing people over time. I'm not sure exactly why. Again, I assume the software tells you that your answer is in fact confirmed. So let's see what everyone says. Well, the majority is correct. It is an unsigned 8 by 8 bit or 8-bit to 16-bit multiplication. Now, if your numbers are signed, you'll have to put in some kind of mechanism to correct that, right? Just saying, but the hardware does this in particular. Anything after that will be, some type of software correction. All right. All right, so let's talk about, oh, hold on. Well, the HC11 is big endian, but the way the accumulator D is put together, the HC11 is treats that accumulator A is the high byte of accumulator D. This has nothing to do with endian, or the way it's, because the endian is only how it loads information from memory. This is, again, a little different. Now, why are they the way they are, I can't say, right? Those are design decisions the engineers did when they built it. I can't say. I don't think there's a whole lot of documentation there about that. It could be legacy stuff to other CPUs. That's entirely possible as well. There's kind of an interesting story. When Motorola built the 68,000, another company basically copied it. And they called theirs, I think it was, I forget who it was. You could find this on Wikipedia though. But then, you know, Motorola sued them, and then the company had to change it all, and then they came up with like again a different number. But you know, there was a whole lot of stealing of stuff way back when. I mean, that stuff still happens now. Maybe you just don't hear about it, but because we don't. It's often companies won't patent processes or their ideas, because when you patent something, you have to divulge everything about it. So they just keep everything secret. But then if that secret gets out, then there's, you know, it's even difficult to kind of sue people to try to get any money from what might have been lost from that, right? So you always have to be careful if you patent something, right? Patents aren't really useful for people. So it's just for memory. Yeah, so the whole idea of big endian and little endian is for memory operations. So when I read something from memory, and again, memory, when we talk about memory, it's always referred to as a byte, right? So even in modern day computers, right, when you talk about memory addresses, it's all referred to bytes. Even though you might have a 64-bit system, right, when it goes and fetches information at byte 0, for example, well, where is the information at byte 0 going to go? Is it going to go in the least significant byte of the register, of the 64-bit register, or the most significant byte of the 64-bit register? That's the challenge. And we still have, again, today, the biggest systems out there are either LSB or MSB. It's not like, oh, there's someone has won this war. Or something has won. It's still going between them, right? There's justifiable reasons why you would pick either or. So yes, the HC11 is MSB, but in this particular case, the question I asked, that plays no role there. Okay. All right. So let's talk about the stack. So you've probably, I don't know if you've heard about it beforehand. Hopefully you heard about it in what's the class called? Oh, it's off the top of my head, or at the tip of my tongue. We call it numerical methods, right? There you go. Or as everyone calls it, the C course, or whatever it is. I did develop that course, and I think those are my slides still being used in that course. I'm not sure, but I did have a discussion in there. Oh, great. So did you get the MATLAB version or the C++ version of that course? Just out of curiosity. Even better. Okay. All right. Well, yeah. Well, I mean, there's different tools out there, right? But in any case, that's good to know. Well, I should warn you that C is the preferred language for electrical engineers, because it does generate the smallest thing. Mm-hmm. So the stack is pretty crucial in programming languages. It's basically it basically makes everything run, right? So as I said before, the stack should be the first thing that's initialized as soon as code is executed. And a lot of programming languages do this for us. We don't know where that is or what's going on, right? It just happens. So basically, the stack is necessary in order to have the CPU remember where it was. All right. So essentially, in higher level languages, before we call a function, all the function arguments are pushed in order on the stack. This is how we communicate between functions. We have what's called a application binary interface, an ABI. And an ABI is a specification on how functions communicate with each other on a particular CPU. Now, why we have that is because we might have different companies who make different compilers. So if you have a piece of code, for example, and use company A's compiler, and I have a piece of code and I use company B compiler, should our code be able to talk to each other? Well, it certainly should. Why not? Right? So we have to have rules on how, well, when I call a function, and I'm using company A's compiler, and company B compiled that code, and they just gave me a binary library. how do I use it, right? And we do this all the time. When you get a program for Windows and you run it, you're using Windows functions. And how do you call those Windows functions? Well, there's a bunch of DLLs and all these things in Windows already there, and we're using that code, but there has to be some rule on how that's done, right? So we generally do all this stack or all this stuff through the stack. This is how we interchange information, right? So we push all of our arguments on the stack, and then the processor, before it jumps to that location, pushes the current programmer on the program counter on the stack. And then the program counter changes based on where we want to, whatever function we're calling. So we haven't talked about these instructions yet, but BSR or JSR means branch to subroutine or jump to subroutine. And these we'll go to that location in memory and we'll run that code. And if you've ever, again, hopefully you've seen the C code before or any other language, where are local variables stored? You write a function, you say, okay, int A or B or something, right? Let me just pull up Notepad here just to remind some of you guys in case you forgot. Apparently my window is ridiculously huge for some reason. Just make this more manageable. So if I do whatever, void main, I don't know if anyone remembers what all this stuff is, but int A, I don't know, float B, something like that, right? Let's change this to int. And I don't know, return 3, whatever it is. Okay, so where is A and B stored? They're actually stored on the stack. So we reserve space on the stack for all of my local variables here. Where else would I put them? I mean, I put them in memory somewhere, but where? I need to kind of keep track of that. And then we end up with problems later, and I'll talk about those if we aren't really keeping track of that well. So if I do pass some things to my function again, you may have seen this in the past, if you've ever looked at C code, but so my whatever arguments are passed, oops, let's see. So this value of this integer is going to be pushed on the stack. The value of this pointer is going to get pushed on the stack, right? And then these things are going to be created and put on the stack. So once all that stuff is there and I actually get to the core code of my stuff where, I don't know, maybe I'll just do this. I'll add to this as I go on, A times B or something like that. Maybe I need to do this. Double C or something, whatever. So before this even runs, all these variables have to be allocated on the stack because I might save something to them, right? It's possible. So all of those variables are created locally on the stack, or all of our local variables are created on the stack. Now, because the stack is in memory, okay, we use push and pull to get to stuff. It doesn't mean I have to use push and pull to read and change things. I can simply look at the stack pointer because it's a pointer in memory, and I can just use that to access these variables directly. So I can say, okay, well, let's take the stack pointer plus, I don't know, plus 3, and that's where A is. And the stack pointer plus 2 is where B is. And the stack pointer plus 1 is what C is, right? I have access to the stack pointer, so I can use it, and I can manipulate it, and I can read information from memory in any order I want. Even though the stack pushes things in order, I don't have to use pop to read values off the stack. I only use pop to remove values off the stack, really. It reads and removes, but I can read without removing, and I can change without removing as well, right? Because it is memory. Okay, so let me just go to my next slide here because it kind of talks about that. So the function has the ability to read the arguments without popping other arguments from the stack. Again, the stack is in memory. We can read it indirectly or directly, right? All right, so our function does its work, and when it's completed, the return value is usually stored in some register. Again, that's based on our calling convention, and we return control back to the previous function. So again, let me go back to my Notepad here. So I kind of do all this work. Let me just change this to C and make this double just to make sure that it's actually correct. So I'll do some operation here, but before I return here, I have to kind of pop all these things off the stack. So C goes into some, again, agreed upon register. And then when I go to return back to my previous caller, I pop all these arguments off the stack. And the one thing I also pushed on the stack was the program counter. So I have a special operation in the CPU that pops the program counter or pops the current value, whatever the stack is pointing to or whatever's on the stack, into the program counter. So when it returns, it goes back to where it came from. So it allows us to remember where we were. Who called this function, right? How did we get here? Where did we come from, right? So that function, and it's usually some instruction called, for example, in the HC11, it's called RTS, which is return from subroutine. Intel uses something that's called RET, R-E-T, for example, which is also a derivative of return, right? So the stack is basically used as a way to kind of move this information back and forth, while still kind of allowing there to be variability, right? Who's using what compiler are you using? Well, it doesn't matter what compiler you're using as long as there's an approved standard of how the information is communicated back and forth. Just like how I talk to you guys, right? How are you viewing this lecture? Well, we agreed on the fact that, well, maybe you didn't agree, but it was imposed on you that you'll be using Blackboard, right? Why can't other people view the lecture? Well, because they're not registered in the class, for example. Right, so we've agreed to that. We have also agreed that I'll be delivering this class in English. Okay, if all this stuff kind of if we kind of adhere to all this stuff, everything makes sense. If something is a little bit off, well, then there can be some problem, right? Okay, so why the stack is kind of really, really important. Well, as I kind of said, it enables the CPU to remember the flow of the program, but it allows the CPU to remember where it was at, what it was doing. But there's something we can do in programming, and I don't know if most of you have seen this in the past, but we can do something called recursion. And recursion allows us to do a lot of really, really neat things and very easily. I don't know if you guys have ever programmed using any type of recursion, but a lot of problems can be solved very, very easily with very few lines of code. But what ends up happening is that there's many instances of a function that's created, and it helps solve whatever the issue is we need to solve. So to make recursion work, if I'm going to call a function over and over and over again, every time I use a local variable, well, where am I going to store that local variable in that function, right? So again, just kind of going back to this function here, if I just called this something else, me or my or me, whatever, right? I could do something like this and say, well, times me, I don't know, something, whatever, just some numbers here, right? And that would be totally legal. But we don't want that when I go into this next function of me that I overwrite A, B, and C, right? I need a place to store it. So because the stack grows as I keep adding things to it, the stack allows me to do recursion without any difficulty. I don't overwrite my variables. Now, someone says, doesn't recursion take extra memory as compared to the equivalent? Yes. So recursion can take extra memory, but it usually ends up simplifying the solution of the problem considerably. Some things are not good for recursion. Like there's the classic function that we often look at when we're talking about recursion is factorial, for example. For example, n factorial is just equal to n times n minus 1 factorial. It's a recursive function. But that doesn't mean you should program it as such, right? You can just do the same thing with a for loop, right? That's one of those types of functions that you can easily implement, using an iterative approach. But recursion does solve a lot of problems, and I'll show you one of them, a classic one that I think is it's amazing how easily it's implemented, and it's the problem is actually extremely hard to do. Okay, okay, I have rarely run into solutions where recursion is recommended, except like linked lists or data structures like that. Oh no, you just haven't you haven't seen a good problem. A good problem is something like this. Here's a good one. I'll just open up another notepad, and again, why is it so large? I don't know why Windows remembers the weird size of my windows. Here, evaluate this. X equals 1 plus 3 times 5 divided by 3 plus 4 times 2 minus, I don't know, 7 divided by 10. And you write a piece of code that parses that. Now try to do it without calling a function or calling. If you write this with recursion, it's actually pretty easy. But if you don't do recursion, then it kind of becomes a problem. It's difficult to do. Okay, a classic one, and someone did mention it, right? So I can write a function that says, okay, well, you start, oh, a bracket, okay, well, call myself again. Oh, a 1, okay. A 1 plus something, okay, what do I have to add? Well, now I call it again. Now this is going to calculate 3 times 5. So when this one comes back, it's going to come back with 15. Then I know what to add to 1, right? But this might then look ahead, and then you have to do this, of course, because of order of operations, things like that. You can automatically even insert a bunch of brackets, just to resolve the order of operations and then process it. Whatever the situation is, this is a lot easier to do with recursion. And the one someone already said is, I'll just pull it up here. I kind of already opened it. Is it here? No, it's here. The good old flood fill or paint bucket tool. I tried doing this many, many years ago without recursion. It's practically impossible. Okay, so let me pull up the good old Windows Paint program. Again, I'm still running Windows 7. There it is, finally. The search found it. I don't know why the search is so slow. Okay, let me just pull this over to my other window here. Okay, so you think, okay, let me draw something quickly. Okay, now because the computer is so fast, we're not going to see it operate, but there, it filled it in. Now you can sit there and say, oh, well, how did it do that? Well, it probably did some kind of raster line scanning, went, sideways, left to right, top down, looking for different edges and finding out how does it, fill this in. And for this object, it's actually pretty easy. Let's try something a little different. Something a little bit more complex. So bear with me here as I try to draw things with my mouse. Okay, so if anyone can start coming up with a non-recursive algorithm to process this, go right ahead. But when I use that paint bucket tool, guess what happens? It gets it pretty easily. Now, it's certainly taking some time, and one thing I always kind of enjoyed when I was younger, watching a slow computer do this, you could actually see how it was actually performing the work. So if we kind of go over here and see what it's doing, you can kind of see, okay, well, it goes downward, it goes down, and then when it can't go down anymore, it goes left, and then when it can't go left anymore, it goes up, and then when it can't go up anymore, it goes to the right, and so on and so forth. So what's actually happening here is we call this function with just this dot here, and then it's recursively calling, okay, well, now go down here and fill this. And then this one says, okay, recursively go down here and fill this. Well, if you can't do that, move to the next step, and so on and so forth. So the actual code, and get ready for the code here, there it is. Okay, so this is basic, like a binary one, right? If it's not the color, let's just assume it's black and white right now or something like that, where there's a clear border. You go down, left, up, right, and that's it. And if you can't do that, then you return. So it does a flood fill again, south of the node, north of the node, west and east of the node, and that's it, and it returns. But the depth of the number of function calls could be the total, realistically, the total number of pixels in the image, which could be in the millions, for example. So the one problem with this routine is it can take a lot of memory. So it doesn't have to be programmed like this. You can be a little bit more creative to stop it, right? Here's another one where you can kind of see, different methods of how it's done, right? There's different types of flood fills. Well, if you consider O being the number of dots, then yes. Or sorry, N being the number of dots. So you can kind of come up with, you don't have to formally use a stack. You can use a data structure that implements a stack type operation where it's not actually, using the stack for this. Okay. I remember I was at this was something we did in way back when I was in high school. We had this computer programming competition. I went to it, and one of the problems was doing a flood fill. And I was killing myself trying to do this because I wasn't doing it recursively. Whereas in fact, the solution was simple recursion. Okay, but again, just to say, you don't have to formally, call the function. You can come up with some method where the data structure keeps track of what it did, and that's often what we'll do. So there's a story, and well, this is true. When the Macs first came out, the first Macs, and if you saw them, one of the tools they had was Mac Paint, which basically looked like this. And when they were displaying it at the keynote, and I don't know if you've ever seen, a Steve Jobs keynote. He goes up there and he's talking about all this wonderful stuff that they did, right? And there was a serious issue. This was, again, behind the scenes, that the standard Mac, the one with like 512 bytes of memory or something like that, or I think it was 128K, it would often crash when you did the flood fill because, again, it needed so much memory to keep track of what it did. So it was very important that the object that he drew on the screen was very simple. Otherwise, if he hit the flood fill and it was too complex, it would have crashed the computer. So the engineers were very concerned, right? That, oh yes, the flood fill works, but only if you have enough memory. And when you're trying to sell a computer and you say, oh, you only need the base model and it does all this stuff, well, that's difficult, right? So there's probably implementations of this that are far more memory friendly. But if you're just talking about this computer, I can't even. Let me just see if I can see how much memory Paint is using. I'm sure it's not a little bit. Is it MS Paint? Yeah. It's using 40 megabytes, which is absolutely ridiculous when you think of 40 megabytes was like the size of my first hard drive. Actually, my first hard drive was 20 megabytes. So just the amount of memory this computer uses is the most storage I had at one point. So yeah, I don't know if I don't think I can erase this and see something, but there's probably some demonstrations out there you can find where it shows the flood fills, kind of working, again, just like this, slowly. So you can actually see how it does the work. But you notice how it went back, again, just going back here when it starts again. You see these few dots it missed initially, or over here on this edge, and how does it know to come back here, right? Because again, it's on the stack. Eventually it'll get to it when it kind of gets back to that point. So I tend to use recursion to solve particular problems, but again, to kind of solve the problem, and then I have to figure out, okay, well, if I'm going to do this in a grand scale, I have to come up with a better implementation of it. Sorting numbers, for example, can be efficient if you use recursion. So you guys have probably heard of the bubble sort, for example, which is the worst sort ever possible in the world, but there's the better sort, which is the quick sort, which is far better, and it's a recursive algorithm. Also, the radix sort is a little bit faster, but again, it's recursive. It usually, if you're just looking at am I looking at the same thing again and again and again in my process, right? That's usually when recursion kind of kicks in. If you're always saying, okay, now I have to look for this situation, or I have to look for this situation, or I have to look for this situation, it's kind of like the same situation, but at different points in your algorithm, then that's where you can usually say, okay, recursion might be useful. But yeah, I don't prefer bubble sorts, but basically because bubble sorts just actively, they do too much memory stuff. And one thing they don't tell you in programming languages today when you learn them is accessing memory is a penalty. So if you have to sit there and say, well, let's come up with an algorithm that accesses the least amount of memory, then it will perform better on a modern day CPU. But that's not something most people think about. That's what slows down computers today. It's when you access memory, because memory is slower. It's just what it is. Okay. Well, 13 minutes left. I don't know, or sorry, it's only 5-ish minutes left. Is there any other questions about this stuff? So, oh, I should just kind of explain it just again a little bit more. So the stack is basically, again, you can look at it as like a notepad of kind of like the steps in what you're doing. So, you know, you always have to look at a computer like it has no short-term memory, because it doesn't. It has no short-term memory. The only short-term memory it has is what you tell it to remember. Right. So if I asked you, oh, you know, come to my house and pick something up, right? Okay, well, you'll say, well, what are the directions to your house, right? So I give you the directions to my house and you write it down on paper. And you follow those directions to come here. And what you'll likely do is when you go back, you'll follow those directions in reverse order to get back to your house, right? You'll probably take the same route back. Well, if you didn't write down the directions or write down how you got here and didn't remember the previous turns, how would you get back to where you were? So that's really what the stack is providing us. It's like it's a trail of things that it did so we can backtrace to get to where we were before. Well, it's a difficult problem teaching someone how to program a CPU. So here we're talking about how CPUs are built, but sadly, you guys don't really have a good solid understanding of how they actually operate. Right, and it's hard because you're kind of you know, it's lack of a better word, but you guys are spoiled in terms of computational performance. I don't think any of you really sit back and sit there and say, well, how does all this work? You know, everything I'm seeing here. How is all this happening? And I think if you had a computer that was extremely slow to begin with, you might have actually been kind of interested in how all these things kind of happen. Now, we don't really think about it. It just kind of all works. Right, so that kind of puts a different point of view on the way you guys look at things. I don't think you'll ever be amazed by technology, just because you see it all the time. But I'm always amazed by this stuff. Every time I see something, I just want to take it apart and see how it works. But it's obviously, you know, ridiculously complicated. Because it's no longer about how things work. It's about making things more efficient. So, for example, a web browser is a very simple thing when you think about it. What makes it complicated is, oh, let's try to make it fast. Let's try to make it secure. Let's try to make it use the least amount of memory as possible. Apparently, they're trying to do that. I don't believe them, but they're saying that we can make it more memory efficient. But you know, all these things, this is how we complicate things. Like how a modern day CPU is built is ridiculous, because it's not about just running the program. It's about running the program as fast as possible. And there's a whole lot of optimizations there that make it do that. Someone says they're amazed at wireless. Yeah, how fast this stuff is moving data. Yes, it is ridiculous. When you consider when I was growing up, I was sending data over a telephone at 30 bytes per second. And you guys are, oh, let me just watch a video, you know, while I'm walking outside. And that video is probably coming in at megabytes per second is the data rate to watch that video. It's crazy. But again, keep in mind that, you know, there's been a whole lot of work that has been done over the years, the reduction of transistor sizes, all these things have come together to make all this stuff possible. And there's, again, when I say work, it's billions of human hours that get this done. It didn't happen overnight. It really didn't. It took a long, long time. So the wireless stuff, you know, why is stuff getting faster? Well, we've come up with better ways to encode it, but mostly because there's more air. There's more wireless spectrum being released all the time. And companies are, you know, again, they're killing themselves to grab it, right? They'll spend a ton of money to get it. But that helps too. But when you need to try to make a radio that uses all that space, and that's effectively what's going on. I don't know if you guys know about Wi-Fi. I don't know if you saw when Wi-Fi started, we used to say, okay, here's my access point, and this is on channel 1, and there's another access point over here, and it's on channel 2, and there's another access point here, and it's on channel 3. The reason we manually put them on separate channels was so they didn't interfere with each other. Now, the latest Wi-Fi doesn't do that. the latest Wi-Fi says I'm going to use everything I possibly can. And I'm going to try to work with other base stations. And if I can't, well, too bad. I'm just going to try to, stick something in here when it's not using it. And that's really what's happening. It's basically trying to use every last ounce of spectrum it can while it has the time to do so. So there's going to be contention, yes, but hopefully they'll work it out and you'll get the information there. And then a lot of things you don't see with Wi-Fi and wireless is that they're constantly renegotiating their communication parameters. It's not like the connection is static. It's constantly changing. The speeds are constantly changing. Things are your frequency hopping all over the spectrum. It's kind of crazy what's going on. So the radios in your phone aren't just like one frequency. They're basically a variety of frequencies to make these things work. They're shifting all over, and just again, they're just maximizing the bandwidth how they can. Well, that's what it is. I mean, no one knows how anything really works. It's just a bunch of standards where so and so says this is the way this works, and if I want to talk to it, I have to read or follow that standard, and that's how it happens. There's not one person who builds a CPU. There's experts in all the little individual parts. So there's a guy at Intel that just builds ALUs. That's all he does. And he's done that for his whole life, basically, just building ALUs. There's another guy who just builds memory controllers, another guy that builds clock multipliers, and that's all they do. And every 3 months, they got to do it again with smaller transistors or under a different set of scenarios or circumstances, and they do it again. And each time trying to make it a little bit faster or a little bit better in some way. And that's what's happened here. What's wireless technology? This whole idea of what's 1G, 2G, 3G, and all this stuff. It's not necessarily a particular technology. It's just it's a what we call a generational shift, where where we've kind of dictated enough stuff has changed where we say it's the next generation. But it's really mostly the same technology. Like 5G is basically 4G with just more frequencies, essentially. The problem over here in the North America is that a lot of the frequencies aren't available. They were taken by the military for many applications decades ago, and they haven't been released. So until the military can sit back and say, okay, we're not using this anymore. And if you know anything about the military, they tend to use very old technology because it's very reliable. Until they can sit there and say none of our stuff uses this anymore, then they can't really give up that frequency range. And now with what we use, we can pack so much stuff into there. I mean, there's still a limitation, of course, but it's not like what they were doing before. When we got rid of TV signals, the original TV signals, when HD TV came into place, that opened up a variety of bandwidth. I mean, tons of bandwidth that have been later used for wireless communication. At some point, we're going to get rid of FM radio or AM radio. I don't think we should, because the receivers are very easy, but the bandwidth there isn't as much as TV was, but still, someone will want to use it for some wireless technology, and they'll give up more things to kind of maximize it. But at some point, there's a limitation. Yeah, most people, when people say I built a computer, they got a motherboard, they stuck it in a case, and they stuck a GPU in the slot and screwed it in. Basically, that's building a computer to most people. Building a computer, like designing from scratch, is a very difficult thing. And again, it's not something that happened overnight. These are just generational changes, epsilon changes over time that made all this stuff work. And believe me, there were a lot of problems initially. With a lot of this stuff, it took a long time before PCI Express worked properly. Like there were a couple motherboards where this one didn't work, and you'll still see this today if you do build your own computer. And when I say build, assemble, you'll find, oh, this motherboard doesn't work with this GPU. Why? Well, nobody cares, because that they no longer build it anyway. They're on to the next thing anyway. You're using obsolete stuff. Move on. That's kind of the way the industry is. They'll fix it maybe in they'll fix that problem eventually down the road, but it's not really a concern right now. Just don't use that system. This is why I prefer buying, like a Dell or a Lenovo or something, because it's, 10,000 people have that same computer. If there's a problem, they'll figure it out. But if it's just yours specifically, it's unlikely it'll happen, where you'll get someone who's actually going to sit down and solve the problem, with some hardware compatibility. So it still happens. There's still hardware incompatibilities, but hopefully you won't see them. Okay, so I guess I'll stop there. So I'll be hopefully posting a new lab today. 8, I think. I'm trying to get them out there so we can get them all done. As I did mention, 10 and 11 will be done on the last week of class, so they'll be in lab only. Just warning you. Just again, because of our time restrictions. And I do have some other, again, like little assignments about ethics and things like that. They'll be small, but they're coming. This is part of the accreditation process. So, all right. Other than that, I think I'll, the last week being those makeup classes, right? 9 to 11. So last Thursday, the class you didn't have, I believe it's on one of those days. I don't know which one it is. Just check the syllabus for that information. Okay, so I'll see some of you at 1 o'clock, and if not, I'll see the rest of you on Wednesday. Have a good day. Talk then.